So now we shall see the results for the LTI system. So for the LTI system, as the title of the slide says, the controllability matrix. So we will going to define a controllability matrix and we will construct some space, some subspace out of that controllability matrix. And then we'll try to compute the reachable subspace and the controllable subspace. So consider the continuous time, linear time invariant system given by this AB, because we are only concerned with the AB matrices, not with the CD matrices, where X is an n-dimensional vector and U is a k-dimensional vector. So for this system, the reachability and controllability gradients are given respectively by this. So we have already defined the gradients in terms of the state transition matrix. Now for the LTV system, we already knew that computing the state transition matrix is pretty much difficult. But for the LTI system, we have some flexibility that we can express the state transition matrix in terms of exponential matrix. Okay, so this is what we have done. We just replace all the state transition matrix from phi to the exponential matrix with a single argument t and tau, t minus tau. Okay, so here we would have, so if you recall, we would have phi t1 comma tau as the state transition matrix. So it would become, for the LTI case, it would become e to the power a t1 minus tau. Okay, so this is what I have written here. Similarly, it would be the transpose. Now, and similarly for the controllability gradient, we could replace with the exponential matrix with a slight change from t1 to t0. Okay, now see here, if I replace t1 minus tau, let's say we replace t1 minus tau by another variable t. So changing this d tau would yield minus of d tau is equal to dt. Okay, now computing the lower and the upper limit of this new integral, let's say t lower would be, I would put t0, so it would become t1 minus t0, and t upper limit would become t1 minus t1 equals 0. Okay, so it would start from t1 minus t0 to 0 with a negative sign because of this part. So replacing that negative sign, we just change the lower and the upper limit from t1 minus t0 0 to t1 minus t0. Okay, similarly we have done here, so that we could compactly write the integrand e to the power at b and its transpose. Similarly, e to the power minus at b into its transpose. Okay, now in addition to that, we define another matrix called the controllability matrix of the pair AB, which is defined by this symbol, which is in the math frac environment, b ab a square b up to a to the power n minus 1 into b, where n is the dimension of the x, and the dimension of the controllability matrix would be, it would contain n number of rows and k into n number of columns. Okay, the multiplication of this k and n. So this provides a simple method to compute the reachable and controllable subspace. Now we already knew from the LTV systems that we can define, or we can compute the reachable subspace and the controllable subspace by computing the images of these matrices. Okay, but having an LTI system gives us more flexibility in representing those results in terms of this specific matrix. And this result is given here, that for any two times t0 and t1 with t1 greater than t0 greater than equal to 0, we have reachable space is equal to the image of the reachability gradient, which is again equal to the image of the controllability matrix, equal to the image of the controllability gradient, equal to the controllable subspace. Okay, this is a very important result. Why? So it tells us many things. First of all, you see these two equal signs which are here now denoted by red. So this notion of reachability and controllability, at least for the LTI system, coincide with each other. Meaning to say, either I can use either I can show the reachability or the controllability, both remains the same. Okay, so if one can go, that is to say, if one can go from origin to some state x1, then one can also go from x1 to origin, which is not or generally true for the LTV systems. That's why we carry out the analysis of both the subspaces. Okay, so because of this, one studies controllability for continuous time systems and neglect reachability. So for the LTI system, we will mostly study about the controllability, but whenever we are discussing for the time varying systems, we'll see the analysis of both the subspaces. Okay. So like, as I said, this is an important result. So we'll go through a detailed proof of these results. So this part we have already proved while having a result on the reachable subspace, and this part is for the controllable subspace. So we need to prove either of this equality, because we know at the outset this is equal to this for the LTI systems. Okay, so again this proof will be done in two parts, because we are here again we are talking about the equivalence of two subspaces. Meaning to say, if there is any element belonging to one subspace, if that element also belongs to another subspace, meaning to say both subspaces are equivalent, and this is valid for all the points in that one particular subspace. Okay, so again x1 belonging to the reachable subspace, which we have already shown is equal to the image of the matrix WR, also implies that x1 also belongs to the image of this controllability matrix. Again, just since it is an equivalence, we will close the path by having a implication otherwise in the another direction, that x1 belonging to this also implies that x1 also belongs to the reachable subspace. Okay, so either of this equality you can prove. We are going to show this part of the proof, because this would be automatically equal. Okay, so let's see the first part. So again, starting along the same lines, that when x1 belongs to this reachable subspace, there exists some input u that transfers the state from 0 to x1, and therefore x1 is given by this one. This is basically comes from the solution of the LTI systems. Okay, so we already know that there exists some u. Okay, now quickly we will recall the Cayley-Hamilton theorem, because we were going to use this result, that for every n cross n matrix A, delta of A is equal to this one should be equal to 0 matrix, where this delta of S is basically the characteristics polynomial of A. Okay, so given any matrix A, we have been computing the characteristic polynomial by computing the determinant of this matrix. Basically, this is delta of S. Okay, now we already know that delta, if I replace S by A, here I would have determinant A minus A. So it would be equal to 0. Now this comes from the Cayley-Hamilton theorem. We won't see the proof of this theorem, but using that theorem, I can write this part, this exponential part, or any exponential matrix by this matrix. So you can take this as an exercise if you have any difficulty to see this equation coming by the application of the Cayley-Hamilton theorem. That what you need to take this as an exercise, that you need to prove that I can express e to the power at as this. Okay, so by the application of the Cayley-Hamilton theorem, we can write this: for some scalar functions alpha naught to alpha n minus 1. Okay, now simply I will put e to the power at here, where t would change from t1 minus t to t1 minus tau. Okay, so here I would have x1, this summation I0 to n minus 1. All these are scalars alpha I, so I can take them on the right hand side also. Okay, so I brought AI forefront and then B matrix coming from here. This whole part, which includes U and these alpha I's. Okay, so I directly replace this exponential term here by this term while introducing some scalar functions from alpha naught to alpha n minus 1. Okay, now see that this part I can write, if I open this summation, this whole part a to the power ib would appear as the controllability matrix, and this whole terms would becomes a vector, individual vector of this alpha functions. I just wrote this summation part into form of a matrix. Okay, now if I represent this as some vector eta, so now we have this x1 is equal to some matrix into eta, which means that x1 belongs to the image of the controllability matrix. Okay, so starting from x1 belonging to the reachable subspace, we have shown that it also implies that x1 would belong to the image of the controllability matrix, right? Let's see the other direction implication. So now we are given that x1 belongs to the image of the controllability matrix. Now we know that if whenever x1 belongs to this image of this matrix, that there exists a vector v, for which I can write this equation x1 is equal to some matrix C into v. Okay. Now we show next that this leads to x1 belongs to the image of WR, which is equivalent to saying that x1 belongs to the orthogonal complement of the kernel of the reachability Gramian matrix. Okay, again we know that WR is a symmetric matrix, so I remove this transpose, which is to say that for all eta 1 belonging to this kernel would satisfy eta 1 transpose into x1 is equal to 0, right? So in the later proof we had seen x1 transpose into eta 1 is equal to 0, right? So just to be clear, in the earlier proof we have x1 transpose into eta 1 is equal to 0, if you recall this. Okay, if you just take the transpose of this equation, you would get this eta 1 transpose into x1 is equal to 0, right? Now x1 I know already is equal to this matrix into v, so I replace this x1 by this. So I just need to prove this equation is satisfied for all eta 1 belonging to the kernel of the WR matrix. Okay, so let's see. So to verify this, so we pick an arbitrary vector again eta 1. So in the proof of the reachable subspace we had seen, so from that proof we will borrow one property. Here we won't be showing that property, so this is just a snapshot. Here this is just a snapshot which I had taken from the other proof, where we started with x1 transpose into eta 1, and then we wrote one quadratic form, and then we showed that this quadratic form is nothing but equal to 0, because eta 1 belongs to the kernel of this WR, right? Which means that WR eta 1 should be equal to 0. By using that property we have implied that it is equal to 0, and this is only possible if this matrix is 0. So I will borrow this part. So this part I have written here only by taking the transpose. If you take the transpose of this equation, you would get eta 1 transpose phi into B transpose, sorry B only without the transpose. So here we have eta 1 transpose. Phi for the LTI system is an exponential matrix into B is equal to 0. Okay, so I knew this already, so I just skipped all this part which we have already proved. So starting from this part, I will take k time derivatives with respect to tau of this equation. So we further conclude that if we take k times derivative, I would have, because of this minus tau, minus 1 to the power k, eta 1 transpose. I would also have a to the power k by taking the k time derivative of this exponential itself, and the B matrix. And on the right hand side, it should also be equal to 0. Now, if I put T1 equal to tau, at tau is equal to T1, I would have eta 1 transpose, a to the power k. This part would be e to the power 0, which is nothing but an identity matrix into B. Right? So the negative sign does not make any sense because we have equal to 0. So I can simply write it eta 1 transpose a to the power k, B is equal to 0. Okay. Now if I open this all k's starting from 0 to n minus 1, this will become the controllability matrix. Meaning to say that eta 1 transpose into the controllability matrix is nothing but equal to 0. Right? Which implies that x1 belongs to the image of WR. Okay, this is what we want to prove, that eta 1 C V is equal to 0, and in this equation we already have eta 1 transpose C is equal to 0. So although we have the non-zero vector V, but this equation is always satisfied. For V is equal to 0, it would definitely satisfy, right? But for non-zero V, it will also satisfy, and this is the complete proof. Okay, so this completes the overall proof of the equation. We can recall the example with which we have started as a motivation. So this is the same example where we have two branches R1 C1 in parallel with R2 and C2 supplied with some voltage U. Okay, so in the previous example we have made a conclusion that the reachable subspace and the controllable subspace are basically the set of alpha times 1 matrix of one vector of 2 dimension. Okay, and which means that the system is not completely controllable. So again, if we compute the controllability matrix for that particular example, we would obtain this. Now that those subspaces we have computed when R1 C1 is equal to R2 C2. So if I put R1 C1 equal to R2 C2 here, we would have controllability matrix is equal to this, right? And the controllability matrix, and therefore we would have the reachability subspace is equal to the controllability subspace, which is, this is the conclusion we had seen in the previous example. Now it is again the image of C, which is again given by some alpha times 1. Okay. However, when the time constants are different, 1 by R1 C1 is not equal to 1 by R2 C2, we had seen earlier that then the system is completely controllable and reachable. Why? Because both the subspaces were equal to R square. Now if I compute the determinant of this equation, we would see that the determinant of this is not equal to 0. Right? So the image of C is the complete space. So these matrices, the Gramian matrices for both the cases, LTV and LTI, and the controllability matrix, particularly for the LTI system, we could compute both these subspaces, which are quite important for the analysis of the controllability of the system. Okay.